Swayam Prabha. Digital India. Educated India.
In our previous lecture for spur gear and design of spur gears, we studied different nomenclatures which are used for the spur gear, and we also studied the contact ratio finally, after studying the arc of contact and the arc of approach, arc of races. In terms of line of contact LAB and the base pitch which is given by circular pitch P and the cos of the pressure angle phi, we determined the contact ratio. And then we were studying the phenomena of interference in the involute profile spur gears, and in that we studied how to avoid the interference. The first thing was by having minimum number of teeth on the pinion, and for the pressure angle 20 degree, the most useful values were calculated using the formula for minimum number of teeth on the pinion to avoid interference, and corresponding to the value of mg, which is the ratio of teeth on the gear to the pinion, Zg divided by Zp, and the pressure angle. So this table gives us an idea about what should be the minimum number of teeth on the pinion for 20 degree pressure angle and the number of teeth on the gear. So 13 should be the minimum number of teeth for 20 degree pressure angle on the pinion, and on the gear it should be 16, and so the maximum gear ratio that can be achieved is 1.23. Similarly, when the minimum number of teeth on the pinion is 14, then 26 is the maximum number of teeth on the gear, and the maximum gear ratio that can be achieved is 1.86. The other values also gives what should be the minimum value of number of teeth on the pinion and the maximum number of teeth on the gear and the maximum possible gear ratio that can be achieved. Now, increasing the pressure angle to 25 degree allows a smaller number of teeth on the pinion. That means earlier minimum number of teeth for 20 degree pressure angle was 13, but with the pressure angle 25 we can have 9 number of teeth on the pinion, and the maximum number of teeth on the gear may be 13, and so the pressure maximum gear ratio may be 1.44. So correspondingly, for the 10 minimum number of teeth on the pinion, the maximum number of teeth on the gear will be 32, and the maximum gear ratio achievable will be 3.2. Now, the other methods of elimination of gear tooth interference are: first, removing the cross-hatched tooth tips, that means using stub teeth. The meaning is, we have this gear tooth which is messed with another gear tooth like this. Now it is clear that if the base circle is of this gear is this one and pitch circle of this gear is this one, pitch circle of this is this one. So it is clear that the portion of the gear tooth below this will be non-involute and this is involute because it is the addendum part and this is the part below the base circle. So, when the contact will take place between this and this, so there will be interference. So, what we do is we cut some portion of the teeth which is going to miss. Similarly, this part is stubbed. So, along the non-involute part of this gear, there will be no contact. The second is increasing the number of teeth on the mating pinion. Then third one is increasing the pressure angle. But increasing the pressure angle has some other disadvantages. When we will do the force analysis, then at that time we will find that the pressure angle increases the part of the load which is not taking part in transmission of the load. So, the transmitted load decreases with the increase in this one. Now, the next we can do to avoid interference is tooth profile modification or profile shifting. The next one is increasing the center distance as illustrated in the coming slide. Method of elimination of interference by increasing center distance. What we do is by changing the center distance, let the earlier center distance is this one, this and this, and we know that by slightly changing the center distance, the fundamental law of gearing is satisfied by the involute profile. So, if the center distance is changed to this one, this is small change we are going to make, shift in center distance. So, by shifting the center distance, what happens is the base circle radius will remain same because this is the circle on which the involute tooth profile is formed. So, this will be unchanged. There will be new pitch circles, okay, and there will be new pitch point. Okay. Earlier the pitch point is this one where the pitch circle, this pitch circle and this pitch circle was touching each other or tangent to each other. This was the pitch point. By shifting the center, now the pitch point has shifted some distance. This is the distance by which the pitch point has shifted. Now the pitch point is somewhere here. Now due to this shift, the pressure angle changes. Earlier pressure angle was 20 degree, then it may change to 20 degree plus some value. So, for this particular example, it is shown that the new pressure angle is 23 degree. Now, we know that with the increase in pressure angle, what happens? The distance between this pitch circle and this base circle, pitch circle moves up, and so the non-involute part will be smaller. Then standard tooth systems for spur gears. To reduce the variations of gear to a manageable numbers, standards are evolved. Standard makes it easy for design, production, quality assurance and replacement, etc. Three commonly used pressure angles are 14.5 degree, which is now not in use, then 20 degree, 25 degree, and sometimes 22.5 degree is also used. The standard gear tooth are shown here. With the pressure angle 14.5, you may see that the base circle is very much above the root circle, and so non-involute parts are more. But with the increase in pressure angle, base circle comes down to the pitch circle, and so non-involute part is lesser. With further increase in pressure angle, the base circle comes down to the pitch circle, and so the non-involute part is very, very small. Now in the case of stubbed tooth, you may see that the upper part of the tooth is stubbed, which has a depth equal to 0.5 of the M. So by stubbing it, what we are doing is we are decreasing the addendum, this addendum, and so there is lesser chance of touching the involute part of addendum with the non-involute part which is below the base circle. Now in this one can have full depth gears or stronger stub tooth gears. Why it is said stronger stub tooth gear means we are reducing the overall height of the gear tooth, and so when the transmitted force will act on this and on this, the bending arm will be smaller for this case, and so it will be stronger. In a standard tooth system for metric gears, addendum A is equal to 1 M, dedendum B is equal to 1.2 M, whereas for the stub tooth gears, addendum A will be 0.8 of the module and dedendum will be 1.0 module. The shorter tooth makes it stronger and its load carrying capacity increases. It also helps in avoiding interference in certain cases. Now the profile shifted gears, interference in a smaller number of tooth pinions can be avoided by having unequal addendum, longer addendum for the pinion and shorter for the gear. These are called profile shifted gears or non-standard gears. You may see here the short addendum on the gear, the addendum is shorter on the gear and addendum is longer for the case of pinion. But we have seen in the standards that the addendum A is equal to 1 times the module. But now here we are changing the module for the case of gear and pinion. So same addendums are not there. For the case of pinion, there is a longer addendum, and for the case of gear, shorter addendum. So what happens is, if the addendum of gear is shorter, and so there is lesser chance of touching the involute part of the addendum to the non-involute part of the mating gear. AGMA defines the addendum modification coefficients as x1 and x2, which sums up to 0, being equal in magnitude and opposite in sign. AGMA is the American Gear Manufacturers Association. This shows you the standard tooth system for spur gears for 20-degree full depth, for 20-degree stub and 25-degree full depth. The values of addendum, dedendum, clearance C, working depth, which is equal to the sum of your this addendum and the depth above the base circle and below the pitch. That will be the working depth. Then hole depth is equal to H, and that is given by addendum plus dedendum, and so this will be 2.25 for the case of 20-degree full depth and so on. Tooth thickness T. Tooth thickness T is measured along the pitch circle. So if this is the pitch circle, then along the pitch circle this circular distance is called the tooth thickness. So standard tooth thickness for 20-degree full depth is 1.571 times module, and so on for the case of 20-degree stub and 25-degree full depth. The face width is 9 times module to 14 times module for the case of 20-degree full depth, 20-degree stub and 25-degree full depth. Face width is actually this one. this is called the face. This is the face, like this. Well, so the face width is given by standard face widths are like this. Then the fillet radius. So there will be fillet. So this fillet radius minimum will be 0.3 times module for all the cases. Then top land is this one. Well, so top land minimum will be 0.25 m for all the cases. Now we will study the forces which acts on different gears when a pair of gear is in mesh. The force is transmitted from one gear to another gear along the line of action, which makes angle equal to pressure angle with the pitch line, and both these lines passes through the pitch point. So let's take pitch circles of two gears. This is the pitch circle of the pinion and and this one is the pitch circle of the gear. Considering the concept of linkages, the linkage corresponding to the point where these two gears rotate is called the linkage number 1. This is linkage number 1, 1, 1, and the pinion is called the linkage 2 and gear is called the linkage 3. So we have pinion represented by 2 and gear represented by 3. This is the pitch point where the pitch circles of two gear are tangent to each other or touching each other. This is your pitch line, and this is the pressure line. This pressure line will be tangent to the base circles and making angle phi with the pitch line. Okay, the pinion is rotating in a clockwise direction with RPM equal to N2, and the gear will rotate opposite to the direction of rotation of pinion, and so it is rotating in an anti-clockwise direction with speed equal to N3 RPM. Okay, now the forces from pinion to gear will act in the direction of line of action. This is the line of action, and so when Figure diagram of pinion and gear are made separately, which are shown in figure B and figure C, then FA2 and TA2 are the force and torque respectively exerted by shaft A against pinion 2. F32 is the force exerted by gear 3, this gear 3, against the pinion. Similarly, if we see the gear, then B is the center of rotation, or it represents the shaft on which it is mounted, and the bearing force is FB3 and the torque is TB3, and the force is shown as F32. Okay. Now this gear is rotating in a anti-clockwise direction, and pinion is rotating in a clockwise direction. Now this F32, which is the force exerted by gear on the pinion, may have a component tangent to the pitch circle of the pinion, which is given by F32 tangential, and the radial component will be F32 radial. Now in a similar way, for the case of gear, this F32, which is the force exerted by 2 is the pinion, on the 3, which is the gear, will have two components, one tangential to the pitch circle of the gear, which is F23 tangential, and the radial component F23 radial. Now it is clear from this diagram that F32 radial will equal to M23 radial, and both of these are acting towards the center of the rotation of the pinion and the gear respectively. And so it is clear that F32 radial will equal to F23 radial. Similarly, F32 tangential will equal to F23 tangential, but the only thing is their direction is different. The direction of F32 tangential is opposite to the direction of rotation of the pinion, and pinion is the driving gear, pinion, and this is driving. So we can say that the tangential component of the driving gear will act opposite to the direction of rotation of the driving gear. Now if we see the gear, which is the driven member, then in this case the tangential component F23 tangential is acting in the direction of rotation of the driven gear. And so a general rule we can apply to determine the tangential load acting on the driving gear and tangential load acting on the driven gear. On the driving gear, the tangential force will act tangent to the pitch circle but opposite to the direction of rotation of the driving gear. But in the case of driven gear, the tangential component of the load which is acting between the two gears in mesh will be along the direction of rotation of the driven gear, and the radial components will act along the axis of rotation or the center of rotation of the pinion and gear in both the cases. Now if we see the tangential component and the radial component, then this tangential component is mainly responsible for rotation of the pinion or the gear. Well, and the radial component is non-productive part. It will apply force on the bearing of the shaft, and so a radial force will act on the bearings due to this radial component F32R or F23R. So the main productive element which is responsible for transmission of load or power from one gear to another gear is F32 tangential or F23 tangential, and both are same. So we can say that F23 tangential is equal to just minus of the F32 tangential. Their magnitude is same, but the direction is different, and this is responsible for transmission, and so we will say the transmitted load WT. So this will be called transmitted load WT, and this will be called the radial load WR. So in place of using the subscript 23 or 32, we can replace or use the subscript only tangential and radial between the two gears in mesh. Now if there will be more than two gears, like if an idler is in between these two, then we must use the subscript 1, 2, 2, 3 like that. So the tangential component is now called the transmitted force. Now from this transmitted force WT, which is equal to F32 or 23, we can find the torque which is to be transmitted. The torque will equal to the transmitted load multiplied by the radial distance along which it is acting. So if it is pinion, then this radial distance will equal to d2 divided by, where d2 is the pitch circle diameter of the pinion, divided by 2. So the torque transmitted or applied torque will be d2 divided by 2 multiplied by Wt. Now the power H which this system is transmitting can be obtained from the formula. The power H is equal to the transmitted load Wt multiplied by pitch line velocity. So if Wt is in Newton, then V, pitch line velocity, will be meter per second, and this H will be in watt, and then V can be given as pi d2 N2. N2 is the RPM. We will divide it by 60 to get per second. Now the unit of this pitch line velocity is mm per second. Now to substitute this into this equation to get V in watt, we have to convert it into meter per second and substitute it here. Now if the units are taken like Wt is in kilonewton, power is in kilowatt, d diameter, pitch diameter is mm, and the RPM is revolution per minute, then the formula will be H is equal to pi d2 N2 Wt divided by 6000. Now let us study what stresses acts on a spur gears. When a pair of gear is in mesh, then we have found the transmitted load is Wt, and Wt is the tangential component of the force which acts along line of action. So knowing this force, or knowing the force which acts along the line of action, now we can find what stresses will act on a gear, and that will be in fact on a gear tooth. So there are two modes of failure: fatigue fracture due to fluctuating bending stresses at the root of the tooth. That means we have found that this is a gear tooth, then the load which acts along line of action is this F32 or 23, whatever we may say. So let F32 is the force which is acting along the line of action. Now it has two components, the transmitted load Wt and the radial load Wr. Okay, so this you may say is equal to W. Now here it is like this. So you can say that due to this force and due to this force, there will be some stresses due to bending of teeth due to this transmitted load WT. WT will have some bending arm and a bending moment will act, and due to that at this section and along the length there will be bending stresses. And those bending stresses will be fluctuating because a tooth will be under engagement along the line of action from a point of engagement A to the end of engagement B with the usual nomenclature which we had used in our earlier study. So along AB there is a contact between a pair of gear teeth. Now after this B point where the gear tooth is disengaged, there will be no force, and so on a gear tooth at certain time force will act and then it will become 0. Then after some time there will be no force, and again when engagement starts at point A, the force will act and it will remain there till the pair of gear tooth is under engagement from A to B, point of engagement to the end of engagement. So this type of fluctuating bending load will act. So this WT will have certain value from A to B, and after B this WT will be 0 for a particular gear tooth. So fluctuating bending load is acting on it. Due to that there may be fatigue fracture at the root of the tooth. Now the second mode of failure will be surface fatigue or the pitting of the tooth surfaces, because when the gear tooth are engaged, then this is the point of contact, and this point of contact will be actually a line contact along the width of these two gear tooth, and along this a value of force W is acting with an angle given by phi. So along the line of action this WT is acting, and this is a case of contact stress. Very high contact stresses will develop along the line of contact along the width, and this will also be of fluctuating nature because the contact stresses will have non-zero value when these two gear teeth are under engagement between A and B, and it will become 0 after this B till again A point will come. So the contact stresses will also be a fluctuating contact stresses, and so surface fatigue phenomena will occur, and that is called the pitting. Now ferrous materials have a bending endurance limit, but some of the materials have no bending endurance. Materials do not exhibit an endurance limit for repeated surface contact stresses. With a pair of gears or gear sets, power is transmitted by the force developed between contacting teeth. So this is the point of contact, and the normal force which acts at the point of contact is given by this Fn. It has a tangential component Ft and a radial component Fr as we studied. And this is the base circle, this is the pitch circle, and this is the pressure line along which the normal force Fn is acting. So along the gear tooth at this point these forces are acting, and the component of Fn is Ft, transmitted force, and the radial force. The highest stresses exist at regions where the lines are bunched closest together in a photoelastic figure. This is the photoelastic analysis, and in this photoelastic experiment, the these rings are obtained, and the maximum pressure will be where these rings are closer to each other, and that is the place where the contact is there and the place of the fillet at the root of the gear tooth. So, the highest stress occurs at two locations. First, at contact point where the force F acts along the pressure line, and B, at the fillet region near the base of the tooth. Now, Wilfred Lewis in 1892 developed a equation for bending stresses in a gear tooth, and that equation is still used with some modifications. Now, figure shows a gear tooth loaded as a cantilever beam. This is a gear tooth. Here is a fillet. Well, it is assumed that the maximum load acts at the tip point, that means at the start point A. At the tip, maximum load acts. This is the case where the QT, the arc of action, is equal to the circular pitch P, and where the contact ratio MC is equal to 1. This is the case of where there is no load sharing and a single tooth is taking all the loads. So, the figure shows a gear tooth loaded as a cantilever beam, because it is assumed that this is the fixed end and this is a type of beam, and at the end a force Wt is acting, or a normal load Wn is acting. This normal load has a component Wt and Wr. Now, to determine the bending stress, what we have done is, from this fillet, let's make a beam of uniform strength like this. Okay. This is the beam of uniform strength, and on this beam of uniform strength, at its tip the tangential load Wt is acting and the radial load Wr is acting. So, it will be just like beam of this type, which is fixed at this location and at this point, and a uniform load is acting all along its width. So, let's resultant of that is given by this force Wt. Well, this is the coordinate system. The thickness of this beam is varying along its length. This is the length along x direction. This is the thickness T. Well, so this beam of uniform strength is taken like this beam, and the width is along this one. Width is along this. Okay, like this. So, the root of this beam is this one or this. This is the root of the beam, which is shown by this dashed line. And at this root, the bending stress will be maximum, and so the bending stresses will also be maximum. Okay? And it is also clear that this beam of uniform strength shown in dashed line is tangent to this fillet, and so at the fillet it is touching tangent to each other. This line, if a line is drawn from this tip tangent to the fillet, then that line is this one. This is tangent to the fillet. This line is tangent to the fillet. Okay. Now, this has a length equal to t. This has a length, means this root has a length equal to t. It is given by here t, and it has a width given by f. Okay, the width is given by f. Width is given by f, a nomenclature used by Lewis. So we have the cross section is t and f. This is a rectangular cross section at the root. So the section modulus for this beam shown by dashed line is given by I divided by C is equal to f t square divided by 6 for this section. So the bending stress will be given by the bending moment at this root, if it is m, and section modulus is I divided by C, then the bending stress at this root will be m divided by IC. M is given by Wt multiplied by this bending arm. Bending arm is L. This height is L. So the bending moment at the root will be, bending moment M will be Wt multiplied by this bending arm L. This is bending moment. Substituting this value and the value of section modulus I divided by C, we will get the bending stress, that is 6 WTL divided by FT square. Okay. Now this terminology T divided by L, the T is the thickness divided by L is the criteria for beam of a uniform strength. So for beam of a uniform strength, the relationship is this x divided by t square should be constant. We will see later on. Now Lewis considered gear tooth as a cantilever beam with static normal force W, this W or Wt, F or Wt. So this figure shows clearly that gear tooth is stronger throughout the inscribed constant strength parabola. This is the constant strength parabola which we had seen in our previous slide also. Okay, except for the section at A, this A, where the fillet is, where parabola and tooth profile are tangential to each other. Now we applied some simplifying assumptions. The simplifying assumptions were the full load is applied to the tip of a single tooth, the radial component WR is negligible, the load is distributed uniformly across the full face width, forces which are due to tooth sliding are negligible, stress concentration in the tooth fillet is negligible. These simplifying assumptions were applied by Lewis because the last one, stress concentration at that time, were not known. The stress concentration factor Kt was not known at that time. or the fatigue stress concentration factor Kf. Now, forces due to sliding are negligible. This analysis was done for the cases where the sliding was negligible, only rolling action was taken. The load was assumed as uniformly distributed along the width. The radial component WR is negligible because WR will apply compressive load, and the compressive load is not detrimental for the fatigue, and the full load was applied at the tip of a single tooth. Now, in our next class, we will study how this Lewis equation was changed into a form which can be used very easily in the design of the component, and then later on we will see. Now, AGMA, the American Gear Manufacturers Association, have modified this Lewis equation to accommodate different other factors. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. You may ask, how do sociologists view religion? Religion is becoming an important issue for our society. Now, sociologists, this is true that sociologists explain one thing in terms of other things of society. So, religion, if you ask sociologists to explain religion, they will explain religion in terms of other things of society like education, economic development. In sociology of religion, there are two major traditions actually. In one tradition, to use language of methodology, in one tradition religion is a dependent variable. In another tradition, religion is an independent variable. What I mean is that in the view of Karl Marx, who said that religion is the opium of the working class, religion is closely associated with contradictions or relations of class in society. Marx believed that as time passes, societies evolve, and this evolution of society is dialectical, like from a classless society to a class society, class formation, and eventually again a classless society will emerge. Karl Marx believed that laws of human behavior or laws of society are specific to stage of development of society and are closely associated with mode of production or tools and techniques of production and ownership of tools and techniques of production. To Karl Marx, who think that a modern society is a capitalist society, religion is the dependent variable which needs to be explained in terms of class relations. And when he says that religion is the opium of the working class, it means that religion is used by the powerful class, the class which owns the means of production, to legitimize their class position or to confuse the workers. Let the workers think that if they are poor, if they are exploited, and if they suffer from various kinds of problems, it is because of their fate or their deeds in the previous births, and not develop the revolutionary consciousness to analyze the real causes of their poverty or exploitation or ill health. This is one view, and religion is the dependent variable, which also means that tomorrow in socialist society or in communist society, if it ever emerges and society becomes classless once again, religion may not exist. Now, according to another view, Max Weber, religion is actually the independent variable that explains emergence of something else, and that something else is the emergence of capitalism. Max Weber said that unlike in the Hindu countries or the Muslim countries or Christian countries where influence of Catholic Christianity was rampant, capitalism as we understand by capitalist institutions, capitalism could not have developed. It does not mean that people, Hindus or Muslims or Catholic Christians, they were not acquisitive in nature, but there was a difference between them and those influenced by Protestant ethics in certain countries of Western Europe, and the difference was that these people did not use what they earned from their enterprises for comforts or for saving or for security or for status or prestige, but whatever they earned from their enterprise, they further invested this in the enterprise itself, and they lived simple life. By living simple life and spending the earnings back in the enterprise leads to emergence of capitalism in Western Europe. Here you see that religion is the cause. So, at some point of time, some philosopher, his name was Calvin, who gave a new turn to Christianity and propounded the philosophy of a new philosophy of Protestantism, also called Puritanism, the theory of predestination, which created anxiety in people's mind to know whether they are elect or not, whether after their death they will go to hell or heaven. So, this reinvesting in enterprise and not using the profits for their own gains or for their own comforts, this produce capitalist society or industrialization, in simple language industrialization, or this produce economic development first in the countries of Northwest Europe. And another issue which sociology tackles with regard to religion is whether we are secularizing. Now, it has been found that in the Western countries with urbanization, economic development, industrialization, education, democracy, there is a fall in religiosity. But in our country, secularization is defined in a different way, because we are a plural society, and for thousands of years all religions have been juxtaposed in our country. So, we define secularization as a process in which state maintains equal distance from all the religions, but does not become irreligious state. So, but this kind of definition or this approach of state obviously is going to raise new issues, new social problems, and religious issues, other issues, but this is what it is. So, sociologists of religion will also study this process of tensions in the process of secularization in a plural country like India. Thank you.
Hi, my name is Gillette Sam, and I teach sociology at IIT Kanpur. Today I am going to tell you about the different characteristics of the movement of things around the world that are associated with globalization. We refer to these kind of movements as global flows. Now, the concept of global flows is quite important, and it's important for us to understand the different ways in which these flows might occur. Now, typically when people talk about the movement of things from one place to another in the context of globalization, they're under the misconception that things tend to flow from abroad into the place where they are living. In a very sort of stereotypical manner, there is this idea that with globalization, much of the movement that occurs is from Western countries into non-Western countries. Now, as sociologists, we know that actually global flows are multidirectional. So, which means that as much as there is a movement of flows from Western countries into non-Western countries, there is an equal amount of movement of flows from one non-Western country to another non-Western country, and in fact, a movement of flows from non-Western countries into Western countries as well. Let's take the example of food, for instance. You may be aware of a type of food which originated actually in China and then goes on to Japan, called ramen. For instance, the popular brand Top Ramen that is consumed in India is an example of ramen. Now, ramen, initially the movement is from China, which is a non-Western country, to Japan, which is another non-Western country. From Japan, this very popular food item travels to Western countries, such as the US, and also more recently to countries in Europe. So there you have a movement from a non-Western country to a Western country. And in fact, now we have very specific types of ramen being consumed in metropolitan centers in India as well. So there's another movement from a Western country to a non-Western country, which is India. So global flows in that sense are multidirectional. A second aspect of global flows is that they could be interconnected. An easy way to think about this would be if you have relatives who are traveling from the US or the UK or Australia, very often you'll see that people request them to carry electronic items with them. They say, oh, can you please get me a laptop, or can you please get me the specific camera lens that I'm looking for. So here you see that the movement of people, which is a person moving from one country to another country, is connected to the movement of technological items as well. So global flows in that sense are interconnected with each other. A third characteristic of global flows is that we could see that they happen in reverse. In fact, they are called reverse global flows. An example of a reverse global flow would be a style of music that you may be very well acquainted with, which is Bhangra. Now, Bhangra music is something that originated, as we know, in the state of Punjab. Now, as you know, Punjab is also a state which has seen a lot of out-migration, not only to other parts of India, but also to other parts of the world. So as people migrated to other parts of the world, they took their music with them. So when people migrated from Punjab to the UK, for instance, they hung on to the music that they were familiar with. So Bhangra moved from little villages in Punjab to the major cities where people from Punjab settled to in the UK. While in the UK, over subsequent generations, this music was transformed. It was not only performed in its original version, but it was also performed with the addition of many different types of beats, which are more familiar to people in the UK. At one point in time, you see that this modified form of Bhangra comes back to India. We're talking about the 1990s to the 2000s. So here you see that that a form of music that originated in India moves out of India to the UK, it is modified a little and then comes back to become extremely popular in India again. So in some ways, this form of music is returning to where it started out, but in a slightly changed manner. We call this kind of movement as a reverse flow.